Alright guys, so here's what we talked about on Thursday and Friday. We found different ways to find delta H of the reaction. There are three different ways that we talked about. Well, kind of four, because there's two types of calorimetry, and then Hess's law and the delta H formation. So we've been doing calorimetry so far that does not talk about delta H. It's just a hot piece of metal or a hot sample of water that goes into a cold sample of water and blah, blah, blah. So anyway, so another thing you can do is you can actually do a reaction inside of a coffee cup calorimeter, which is a question like this. So like 50 mils of 0.1 molar silver nitrates added to 50 mils of 0.1 molar HCl in a calorimeter. If the temp rises from 22.6 to 23.4, what's delta H for the reaction in kilojoules per mole of AgCl? If the C for the calorimeter is 19 joules per degree C. So still we're using the same equations. Q of the system is equal to negative Q of the surroundings. So the system this time is the reaction and the surroundings are the water and the calorimeter. So the reaction we don't know as of yet, but we know everything about the water and the calorimeter that we need. We know S, M, and delta T, and we know C and delta T. Now the M, the mass of the water, comes from the total volume from the reactions. We had 50 mils and 50 mils. For water, 1 gram is equal to 1 mil. Now, true, these things are solutions and may not be exactly the same as water, but they're close enough to not really matter. So anytime you have a problem like this, just the total volume of the solutions is the same as the mass of your water. So the mass is equal to the total volume of the solutions. So anyway, you know all that stuff, and when you multiply and all that stuff, you get negative 350 joules. So delta H is going to be the kilojoules per mole, because that's what it asks for, kilojoules per mole of AgCl. So we change our joules to kilojoules and we put it up on there on top. Now, for the moles, we need to figure out the moles of silver chloride that were in the reaction. So we do that by using the volume times the molarity, because the molarity is really the moles over the liters. And if you have moles over the liters cancel out. And so we multiply those two, we get 0.005 moles. And so because there's 0.005 moles of silver and 0.005 moles of chloride, they make, at the end, 0.005 moles of silver chloride. We can assume it goes to completion. And so that's what goes here on the bottom, because that's the moles of AgCl, and that's what it asked for, kilojoules per mole of AgCl. So the delta H for the reaction is this number divided by that number, and we get negative 70 kilojoules per mole. So that's one way we can find the delta H. And that's for finding the delta H of an aqueous reaction, a reaction that does not have any gas components, because if you have gas components in the reaction, like a combustion reaction, then you're going to have work being done if you allow that gas to escape. So you would have to do something like bomb calorimetry, where there's no change in volume in order to get, in order to have the delta H for that. So anyway, second thing, constant volume calorimetry, sometimes called bomb calorimetry. So how to do problems like this, these go in two different parts. Here's the first part. A bomb calorimeter is calibrated. You pretty much have to calibrate a bomb calorimeter every single time you use it. So calibrated by burning 1.890 grams of benzoic acid. Benzoic acid has this formula, and here is the delta H for that combustion reaction. Benzoic acid releases 3227 kilojoules per mole of benzoic acid. The temperature increases by 8.32 degrees C. Determine C for the calorimeter. So, again, Q for the reaction is equal to negative Q for the calorimeter. One thing that's different about bomb calorimetry is we don't separate the water and the calorimeter. It's just negative Q for the calorimeter. So the calorimeter is the entire surroundings. So we know the stuff over here, we know Q for the reaction because we know the mass and we know the delta H for that reaction. So we have to include this term though, because this is the grams. We've got to convert grams to moles and then moles to kilojoules. So this is the molar mass of benzoic acid. So we go grams to moles, and then this is the delta H. That tells us how many kilojoules there are per mole. Sometimes delta H's will be in kilojoules per mole. Sometimes they'll be in kilojoules per gram. So just pay attention to what the units are down here so that you know whether you have to include this grams to mole conversion. So when we multiply and divide, we get negative 49.93 kilojoules. And so that's Q for the reaction. So that goes on this side. Then Q of the calorimeter is C of the calorimeter times delta T. And we know delta T from the problem, so we can simply solve for C for the calorimeter, and that's 6.00 kilojoules per degree C. So that is the first part of a question. And then in the second part of that same question, you would have the actual testing of the unknown. That's what bomb calorimetry does. You figure out the delta H for combustion of various substances, or the food content of various substances. So 0.5 grams of naphthalene, which is C10H8, is burned in the same bomb calorimeter with an initial temperature of 20 degrees Celsius. If the final temperature is 26.4 degrees Celsius, what's the delta H of combustion for naphthalene in kilojoules per mole? So we have the Q of the reaction is equal to negative Q for the calorimeter, because again, we don't separate out the water in the calorimeter. Now we know C for the calorimeter, and we know the temperature change. We're subtracting the two, and so we can get Q for the reaction, which is negative 38.4. And like we said before, delta H is kilojoules per mole. So that's the kilojoules. It was already in kilojoules because the C for the calorimeter was already in kilojoules. And now we just need the moles. And the moles are much easier because they're just grams turned into moles. So we have the grams, and we are going to convert from grams to moles by dividing by the molar mass. So we have the molar mass of naphthalene, and we convert to moles. Moles go on the bottom, and we get 0.9844 kilojoules per mole for that one. The third way that we find delta H for a reaction is using Hess's law. So in Hess's law is the idea that you can add together reactions, and the sum of the reactions, the sum of the delta H's for those reactions will equal the delta H for the sum of the reactions themselves. So if we want to find this reaction, we want to find the delta H for 2B solid plus 3H2 gas reacts to form B2H6 gas. What is the delta H? Using these four reactions, we can manipulate these reactions and subsequently manipulate their delta H's in order to find the delta H for that reaction that we don't know. So the way that I enjoy doing this, the way I like doing this is if you just build your reaction, and by that I mean just focus on the parts of the reaction that you need. So for the beginning, we need 2B solid. So we would use A. So I'm just going to write down here, 2B solid plus 3 halves O2 gas reacts to form B2O3 solid. And the delta H for that reaction is negative 1273 kilojoules. So that gives us B2 solid here at the beginning. So we have that part of it. Next we need 3H2 gas. And so we look for one that has H2 gas in it, and only C has H2 gas. But we need 3 of them. So we need to multiply this entire reaction by 3. And when you multiply an entire reaction by 3, you also have to multiply the delta H by 3. So here we multiplied the entire reaction by 3. It was 1 half O2, so that becomes 3 halves O2. And we had to multiply the delta H by 3 as well. So we now have these two. We have the boron and the hydrogen, and now we need the B2H6 in the products. And so the only thing that has B2H6 is this, and it's in the reactants. So we need to get this in the products, and we do that by reversing the entire reaction. So we reverse the entire reaction, the products become reactants, the reactants become products, and when we reverse a reaction, we have to change the sign of that delta H. So negative 2035 becomes positive 2035. Okay, so then, once we've built the reaction, we have this in the reactants, this in the reactants, and this in the products, then let's see if everything else cancels out, because a lot of the time they will. And just forget we saw that last one. So we have these three. And so let's see what cancels out of these. We have B2O3 solid here, and we have 3 oxygens here and here. This 3 oxygens cancels out both of these. 3 halves is 1.5 and 1.5, so 1.5 plus 1.5 is 3, so this oxygen cancels out both. We cannot cancel out this 3H2O with this 3H2O because this one's liquid and this one's gas. They have to be of the same phase in order to cancel out, which means we need this last equation. So we need 3H2O gas on this side, and we need 3H2O liquid on this side in order to cancel those two out. So we need to multiply this reaction by 3, like we do right here. So 3H2O liquid will cancel these two out, and 3H2O gas will cancel those two out. So almost everything cancels out here except for 2 boron plus 3 hydrogen gas reacts to form B2H6 gas, and that's what we want. And we find the delta H by simply adding all of these together. The ones that we multiplied by a factor, we also multiplied their delta H's by a factor, and the one that we reversed the sign. And this one didn't have either of those, so we just used the delta H as it is. And so when you add up all of these, you get 36 kilojoules per reaction, or per mole, whatever. All right, the last way to find the delta H for a thing that we need to talk about is using the standard heat of formation. So this little circle up here means in the standard state. So the heat of formation would be just delta HF, and the standard heat of formation would be this little circle that we have up here. Okay, standard state means that all pressures are 1 atmosphere, all molarities are 1 molar, and the temperature is 25 degrees Celsius. Why they did not have it be the same as standard temperature, which is 0 degrees Celsius, I don't know, but whatever, that's the way it is. So if we have a reaction like this, and we want to find the delta H of formation, or the delta H for this reaction, not of formation, we can use the delta H's of formation of the things in there in order to find it. And the way we do it is this. So if you have the delta H, or if you want to find the delta H of the reaction, it is the sum of the delta H's of formation for the products minus the sum of the delta H's of formation for the reactants, multiplied by their stoichiometric coefficients. So the stoichiometric coefficients become significant. So, like this, delta H for the reaction is equal to 4NO2, because that is one of the products. That is the product up here, 4NO2. So it's the product. So we multiply 4 times the standard heat of formation for NO2, plus, because this is the sum, 6 water liquids here. So 6 times the standard heat of formation for water liquid, so that goes there, minus, because it's a minus, the sum of the standard heats of formation for the reactants. So the first reactant is 4NH3, and so we do 4 times the standard heat of formation for NH3, plus 7 oxygens, 7O2. Notice there is no oxygen over here, and that's because the standard heat of formation for any element in its standard state is defined to be 0. So any element, whether it's oxygen or hydrogen or scandium or titanium or zinc or whatever, any element in its standard state is defined to be 0 for the heat of formation. If it's not in its standard state, or if it's not in its regular form that it's found, for example, if this was O3 rather than O2, it would not be a 0 heat of formation. So only O2 gas has a heat of formation of 0. So when we crunch all that together, we just add it all together, we get a delta H for the reaction of negative 1396 kilojoules per mole. So that is how to use standard heats of formation. We'll go over that and lots of other stuff again, and quiz will be on Monday on that stuff and maybe the stuff from previous in the week.